Alright, I don't think I've made a video for like almost a year now, but I'm excited to make this video. This is going to be the first part of maybe like 3 or 4 parts, but this video is going to be about this MATLAB script, or maybe like 2 or 3 MATLAB scripts that I've made um, that cover different characterizations of 3-phase inverters driving different characterized loads, and I guess the third part is going to be about driving a synchronous motor as a load, but I won't get too ahead of myself. I'll start right now with this first video. This first video, I think I'll just cover how the 3-phase inverter works basically, and how I'm plotting characteristic waveforms of a 3-phase inverter in MATLAB right now. So the purpose of this first script is actually to input, I guess I say RPM of motor here, but you can just change whatever fundamental frequency you want for your load. But basically this script, the end goal is to plot the waveform of the DC link voltage and the DC link capacitor current given a load and given your input parameters. So I guess I'll just go through the parameters right now. So this first parameter is the capacitance of the DC link cap in farads, which I don't think I'm going to get to the DC link capacitor current in this first video. I'll probably do that in the second video. But then this next parameter is the phase current, and this is going to be for a 3-phase load. So this picture shows a 3-phase inductive load and different switching states that I'll get to later. So this parameter is going to be the individual phase current in amps peak. This is going to be RPM if you are driving a motor as a load, and then this is going to be the poles of the motor. Basically the fundamental frequency, the electrical frequency of your 3-phase load is going to be the RPM of the motor times the number of poles, not pole pairs, number of poles divided by 120, and that's converting from RPM to Hertz electrical. But if you don't want to use this script for a motor, I guess you can just put in whatever value you want right here for the fundamental. So then this is the RPM, this is the poles, and then this will be the modulation index, I guess for sine PWM, and this would be the modulation index for third harmonic injection, which I guess also space vector PWM. So this modulation index is basically a way to convert your DC link voltage to the peak output voltage of your converter or inverter. I have it in here actually. This is the with motor parameters as the load, which I'll get to in the third video, but here you can see the modulation index actually determines what your peak output voltage is, and it's different between third harmonic injection and sine PWM. So I'll get to that in the third video though. So modulation index for sine PWM, modulation index for third harmonic injection, fundamental frequency. This will be the switching frequency of your inverter, 3-phase inverter. This will be the switching period, so that's just the inverse of the switching frequency. This is the DC link voltage of the 3-phase inverter. This is the power factor of the load. So for a purely resistive load, it would be 1. Or for a motor, I guess not necessarily purely resistive, but a motor will, I'll get to that in the third video. Purely resistive load 1, purely inductive load would be 0, which is a, so then the phase shift that would account from the power factor is going to be the inverse cosine of the power factor. So let me just run this script real quick. Kind of takes a while to run, but with a power factor of 1, the phase shift between the voltage and the current of the load is going to be the inverse cosine of the power factor. And for a power factor of 1, that phase shift is going to be 0 degrees. And for a power factor of 0, that phase shift is going to be 90 degrees. Then these variables are going to be the number of DC link caps, and then this variable is just getting the total equivalent series resistance of the DC link. So this would be the equivalent series resistance of 1 DC link cap. So this is in ohms. Maybe I should write that. Ohms. Write that here too. And so for this example, I guess it's 1 milliohm, and then the equivalent series resistance of all the caps is going to be the ESR of 1 cap divided by the number of caps, since they're all in parallel. This variable is just representing 2 fundamental periods of the sinusoidal load. So the fundamental frequency, the inverse of the fundamental frequency is going to be 1 fundamental period, so then multiplied by 2, because I want 2 fundamental periods in my plot right here. N is going to be the number of discrete samples in the waveform, so we're going to generate a bunch of waveforms using a bunch of for loops in MatLab, and create a bunch of arrays. So for example, this is going to be an array that is storing the instantaneous current of 1 phase of the load. So you can see 24 or 240,000 samples. So I set n equal to 240,000 samples. And then the time step, that's going to be the amount of time that passes in between each sample. So if I have 2 fundamental periods and it's 240,000 time steps, then 1 time step is going to be equal to the 2 fundamental periods divided by the number of discrete samples that we have. So this first plot is just simple. It's just going to be creating right here. T is going to be an array that is storing the time samples, and then IA, IB, IC is going to be storing the current samples at each step in the array as well. So for a 3-phase sinusoidal load, we're going to have IA is going to be the peak phase voltage multiplied by sine of 2 times pi times the fundamental frequency in hertz times time. It's multiplied by 2 pi because that's converting to radians, and then multiplied by time. And for IB, it's going to be the same, but phase shifted 120 degrees lagging, And then for IC, we have the same, but shifted 120 degrees leading. So then here, I'm just plotting these three-phase currents just to see what we're going for. So this plot of these three-phase currents is basically the current we're driving in our load. That's going to be part of this, I guess you can call simulation. So you can see three-phase sinusoidal, peak value of whatever we input. What did I input? Yeah, 100 amps peak. Peaks at 100 amps. And then now we're going to figure out how do we switch the inverter such that it outputs this current that we're looking for. So we're basically determining what voltage do we need to apply to this load in order to generate this current, and then how do we generate that voltage by turning on which switches. So this picture just shows the different switching states you can have, and using PWM we're just switching between all of these states in order to create a fundamental voltage that will, when applied to the load we've determined, will apply the current we want. So here I'm generating a triangular carrier and modulation sine waves in order to determine the PWM later. So here we have this function is basically just creating this triangular carrier. So based on the switching frequency, we're going to create a triangular carrier. Let's open it. You can see this is a really hard to see sine or triangle wave right now. Zoom out. Can't zoom out. Zoom in. So here you can see the triangle wave that's being generated, and the frequency of this triangle wave is the same frequency as our switching frequency. And you can see these other waveforms are the modulating sine waveforms and the modulating third harmonic injection waveforms. And how do we generate those? For the sine waveforms, the modulating waveform is basically just going to be the modulation index multiplied by sine times 2 pi times the fundamental frequency times time, plus whatever phase shift we get due to the power factor. But since our power factor is 1, our phase shift is 0 in this case right now. And then for the third harmonic injection waveforms, it's a little more complicated. We have the same component where we have sine times 2 pi times the fundamental times time plus the phase shift, but then the third harmonic is basically going to be the same term added into all of these equations, and that's going to be 1/6 of the magnitude of sine times 2 pi times 3 times the fundamental. So it's 3 times the fundamental frequency. That's why it's called third harmonic injection, because it's 3 times the fundamental frequency. And then plus 3 phi, you just have to multiply 3 phi in order to get the correct phase shift on the third harmonic. And then do the same thing for A, B, and C. And then, like the plot I just showed, the red is the switching triangular carrier, and then the other waveforms are the modulating waveforms. And you can see the third harmonic waveform has a third harmonic, and the sine PWM is just one frequency of a sine wave, one frequency fundamental. So then now that we have the triangular carrier and the modulating waveforms, we can determine what state each of the switches needs to be in. So basically, based on our triangular carrier and our sine modulation, whenever basically you can see here, whenever the triangle wave is less than the modulating waveform, then we're turning on switch 1. And whenever the triangle wave is greater than the modulating waveform, we're turning off switch 1. So switch 1 corresponds to this switch, which is complementary to the low side switch. So whenever the triangle wave is less than the modulating waveform, the high side switch is on. And whenever the triangle wave is greater than the modulating waveform, the high side switch is off, and the low side switch will always be complementary to it. So whenever this switch is on, this switch is off. You can see in this case, whenever a high side switch for one phase is on, the low side switch for the same phase is always off. And then we apply the same relationship for the triangle wave compared to the modulation for each phase. So for sine modulation, we have this plot that we saw earlier, and then we have the third harmonic injection modulation, and it's the same case where whenever the triangle wave is less than the modulating waveform, we're turning on the high side switch of the phase. And then here I'm sort of just showing the voltage vectors that we're in. So you can see there's 6 different states that create a voltage vector, and then there's 2 states when all the high side switches are on or all the low side switches are on, then there's 0 voltage vector. And so you can see from this photo, these are the 6 different voltage vector states, but you can imagine if all the high side switches are on, then the potential at each of these pole voltages is the same as if all the low side switches are on, the potential at all of these pole voltages is the same. So there's going to be no current applied to any of these loads, or there's going to be no voltage across any of these phases basically, and there's going to be no driving potential. So here I'm just showing which state it's in over time. It's kind of a hard graph to really look at, honestly, but you can see that it's constantly switching between all of these states in order to modulate the pole voltage. And let me actually simulate it with a modulation index of 1. So if we change the modulation index to 1, I'll show you the comparison between the triangular wave and the modulating waveform, and they're going to be at the same peak magnitude. So once those are at the same peak magnitude, you'll be able to see that the 0 vector state happens less frequently. And we'll be able to see that in the vector state plot once it loads. And how I'm doing all these plots isn't super important, but it's just MATLAB syntax and just setting like y limits if I want them, and labeling the axes and deciding what I'm plotting. So this is basically saying plot the vector of t on the x-axis time from array index 1 to n over 2, and then plot this pole voltage from 1 to n over 2 in the array as well. So then I'm also determining the pole voltages here. So the pole voltage is basically the voltage at this phase connection relative to the DC link minus for A, B, and C. This is A pole voltage, B pole voltage, C pole voltage relative to HV minus, DC minus. And the pole voltage is going to be equal to the state of the high side switch times the DC voltage. So you can imagine whenever this switch is on, the voltage here relative to here is going to be whatever the voltage on the DC link is. And then whenever this switch is on and this switch is off, the voltage here is going to be 0 relative to the HV. This is going to be the same potential as the DC link minus. So we're basically switching this node relative to HV minus from 0 to HV minus, 0 to HV minus super quickly. And the same for A, B, and C. So then I change the modulation index for sine to 1. So here now you can see the sine modulation is going all the way to 1, same as the triangular carrier. And then the voltage vector states they're still going to those 0 vectors, but if we overmodulate, it'll get rid of some of those 0 vectors. But you can see it's going to one of the 6 vectors more frequently now. One of the 6 active vectors more frequently now. And then, so this is determining what the pole voltage is based on the high side switching state. So then this plot, you can't really tell what's going on. Like I said, the voltage is going between 0 and HV plus, 0 HV plus, 0 DC plus, 0 DC plus. But because of the way PWM works is when you're modulating at the switching frequency, you still have a component of this waveform that is at the fundamental frequency. So let's see, PWM inverter harmonics. So you'll be able to see basically the frequency distribution is going to be whatever your fundamental frequency is, and then you're going to have harmonics at the switching frequency. So here you see the fundamental frequency is going to be the main component of this, and then there's going to be harmonics at multiples of your switching frequency. So then I used this moving average window. I tried using this like Kaiser order low pass filter, but you need a signal toolbox for that, so I couldn't use that. But this moving average filter is going to filter out all the high frequency from this, and then I'm going to plot the pole voltage for phase A using sine PWM and third harmonic injection PWM. And here, now you can see, after filtering that out, the blue is actually the pole voltage, and you can see it's at the frequency of the fundamental. And because the power factor is 1, it's in phase with the sine wave created for the current. And then for third harmonic injection, it didn't really filter out the switching frequency enough, but that's okay. You can see, it just proves to you it has this third harmonic in it, and it's in phase because the power factor is 1. And then let's see what happens when we change the power factor to something else. We can try, let's try modulation index 0.8 for both of them. and then power factor of 0.6 and run that. So all of these concepts might be a little bit unfamiliar if you haven't ever studied power electronics or switching converters and switching inverters, but hopefully you can follow the main concepts and understand what's going on with how we're driving the load at least. So let's see what happens when we increase the modulation index and decrease the power factor. So what we expect to see is with a modulation index of 0.8, our pole voltage is going to be it's going to be peak to peak 0.8 times the magnitude of the DC link. And then with a power factor of 0.6, the cosine inverse of 0.6 should give us a phase shift of, what phase shift is that? Calculator. Like 60 degrees? I'm not sure. 30 degrees? Trigonometry. I don't know if cosine inverse. Okay, let's just see what I plotted. Phi is, oh, that's in radians. 0.9273 radians. 0.9273 times 180 divided by 3.14. Like 50 degrees or something. Okay. Anyways, so we should have a phase shift of 50 degrees, and for this the way I have it set up, I'm assuming that the power factor, when it deviates from 1, I'm assuming that that means the load is inductive, not capacitive. So what ends up happening is the current ends up lagging the voltage, and the current lagging the voltage basically means the current phase is, or the current is the same point in the sine wave for the current is going to occur later in time. So it's a bit like confusing to think about leading and lagging, because when you look at the plot, you see the current is to the right of the voltage, which means it's lagging. But just from reading left to right, you think the current being on the left would mean it's lagging, but the current being on the right means it's lagging because it's happening later in time, So now you can see I changed the modulation index to, oh, this isn't what I want to look like. We changed the modulation index to 0.8. So you can see for the sine PWM, the modulation waveform ends up being 0.8, but for third harmonic injection, the modulation index is 0.8, so the fundamental of this waveform would go up to 0.8. Then because we have the third harmonic, it changes the peak of this waveform. And then we also changed the power factor to 0.6, so then, and we're assuming it's an inductive load, so then the current ends up lagging the voltage, and here you can see with sine PWM, this is the pole voltage, and this is the current. phase current. And then for third harmonic injection, we see the same phase shift, but we have a third harmonic. And what ends up happening with third harmonic injection is you have this third harmonic component in all three phases, but that ends up applying this third harmonic on the waveform of the neutral in a Y-connected load. So you can see this is a Y-connected load. This voltage between neutral and ground actually ends up being the third harmonic. So then when you look at the phase voltage for each load, it basically subtracts out that third harmonic. Let me see. I can show you in Desmos, actually. I have a plot. So here I'm showing these third harmonic injected three-phase waveforms, and then this purple is actually the voltage at the neutral node in the Y-connected load. So then if you know the voltage at the phase, which is the pole voltage, you know the voltage at the neutral node, then we can just take the voltage here, subtract the voltage here, and we have the voltage across the phase, right? So then we take, basically this equation is we have the voltage of the pole, this is the pole voltage, and then we're subtracting the neutral node voltage, and then we get this phase voltage. And you can see the phase voltage peak actually goes above the peak to peak of the pole voltage, and that's why third harmonic injection of space vector PWM is advantageous, because if you're driving a motor as a load, or even if you're not driving a motor as a load, you can get a larger peak to peak phase voltage across your individual load compared to the DC link voltage you have. So it's a bit of a little magic trick, sort of. And I think for now I'm going to pause and wait to make part 2, and I'll probably continue after this and upload it at the same time, but I am guessing this video is getting a little long at this point. But part 2 will go over, it'll be basically be using the switching states of these high side switches as well, and then we're going to make a plot of what the DC link current into this inverter actually is. And I'll save that for the next part.